Good afternoon, sir.
Good evening, sir.
Hello. Now is it audible?
Yes, sir.
Yes,
It's
sir.
audible, sir.
Yes,
Yes,
sir.
sir.
Okay. This is the issue.
Great, sir.
All this. So now can you see my screen? Is the
Yes, sir.
screen is the screen visible? Am I audible to everyone?
Yes, sir.
Audible, sir, and
All right.
visible, sir.
So what we were doing is this basic probability is there. So in this case, we had taken this example from yesterday's class, that a class of 14 students, which is the distribution given to you like this. So we had calculated some of the probabilities. Now we're proceeding further along that direction. We have the most probable age. Now most probable age is the age with the maximum probability. Okay. Maximum. Now this is a very important, you'll be asked in some questions, okay, in quantum mechanics also, that what is the most probable value of some quantity. Now in that case you have to find out the quantity with the maximum probability. So in this case this has the maximum occurrence. All right, so this will have the maximum probability. So 25 is the most probable age. Now median age is what? What is the median age? Median age is something where you have that at that value, like above that the probability is same, below that the probability is same. All right, this is that value of the of that is this is the that age, like probability of having a higher age and probability of having a lower than that age is equal. All right, so in this case we have the answer is 23. So if you look at it, like below above 23, this is if you the 23 will come like in between this. So above 23, how many are there? This is 4, 9. Oh, sorry, I made a mistake here. So 23 will come here. 23 will come here. Okay. So above, like below this, there are 7 like 7 candidate students available, and above this there are 7 candidates available. All right, 7 students. So this is the median age. Okay. Now in this case, mean or average, mean or average. All right, mean or
So
average.
how you calculated, sir, median age?
You have to just look at the graph and make the observation. If you see the graph what we had drawn last class, which is very ugly to look at, but let's use this. All right, if you see this graph, so if you see this graph, let me paste it somewhere here. All right. Oops. Let me paste it below. So in this case, yeah. So in this case, if you observe carefully, the 23 mark will be somewhere here. 23 mark will be somewhere here, right? This is 23. Now, if you see, like this is 23, right? This is n equal to, sorry, not 10, age equal to 23, j equal to 23. Okay, this is j equal to 23 line. Now, median is defined as such a way that the probability of getting a lower than this value is equal to the probability of getting a higher value than this. So if you can see the probability of getting a age less than 23, that is what this 1 2 3 4 5 6 7, so 7 by 14. And in this case, in this side also you can see the probability of getting an age 23 higher than 23 is 1 2 3 4 5 6 7, 7 by 14. So this is also 1 by 2, this is also 1 by 2. All right, it need not be 1 by 2. All right, so this is the median age. Okay, now mean or average. Now this is written as like this, 2 angular brackets, mean this is the notation. So in this case, we'll like what is the how many of them have age 14? 1. So this is how we'll write like this. This is 1 into 15 plus 3 into 16 plus 2 into 22 plus 2 into 24 plus 5 into 25. All right. By total number of students. Now this is equal to 21. If you calculate it, it is equal to 21. Or we can write like this. We can write this as Pj, probability of getting a age j into j. So this is how it's defined, the mean of a quantity. All right. Now you have to remember this thing, and this is very important from quantum mechanical point of view. This is summation j pj. All right, so this is the mean of a value defined. This is how it's defined. So this is also called expectation value in quantum mechanics. This is also called expectation value in quantum mechanics. All right. Now this is nothing but the mean. This is actually the mean or average value. Now quantum physicists call it expectation value. All right, so this is an important point to remember. All right, now next is we can similarly define mean of different quantities. Like if you want to define mean of j square, okay, if you square the ages and then sum and divide by total number of students, so you can get the average of j square. This is defined as, the process is same, like you had j here and you had j here. So in this case we have j square here, so we'll write instead of j we'll have j square here now, but this will remain the same. The formula remains, the probability of getting that value will be the same. All right, so this is another quantity. This is how you write for a mean of a j square. All right, now for any given function, now we can generalize this idea. For any function of j, the mean or expectation value, is given by now we are generalizing this idea, these two formulas. Okay, so we can write like this, that if any function of j is there, okay, let's call it f of j, and we take the mean, so we simply like we had put, this was j square, we had put j square, there was g and we had put j here, so in this case we'll put f j and then we have pj. All right, so this is the general formula for finding the mean of any function. All right, so we sum over all the values of the function and along with their probability. All right, so this is a thing which we'll be using during the course. All right, now we let's see something which we'll be using in our uncertainty principle. So there's something, just tell me, there's an example I'm showing you. You have to tell me what is the difference between them. All right, so let me try to draw the graph this time straight. So this is nj. All right, this is j. Now 1 2 3 4 5 6 7 8 9 10. This is 1 2 3 4 5 6 7 8 9 10. All right, so this is j, this is nj. Now we have this distribution. All right, so we have this distribution, and further we have this 1 2 3 4 5 6 7 8 1 2. So 1 2 3 4 5 6 7 8. All right, the graph goes higher. Now in this case, on the other graph is like this. So let me just replicate this graph. All right, and put it here. So in this case, we have everything is same. Now we'll see what if I change these values. If I change this value, okay, to something like this. This is how the graph looks like now. All right, now in this case, what is the what are the differences? Like see, if you're not speaking, then please like mute yourself. You cannot every time tell you this. All right, So in this case, if you have this graph, so what is the common thing? What are the common things between these two graphs? These are the histograms. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and here also 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, the number of values are same. What is the mean? What is the mean? Hello, is anybody home?
Yes, sir.
What is the mean in both the graphs? Are they equal or unequal?
Sir, both will be equal, sir.
Mean will be equal, median?
Little different, sir.
Median is also equal, right?
Equal, sir.
Equal, because this side also, if you take this value, median like 5.5 kind of value, so below this there is only one, below above this there is one, so these are equal, right? So median will be 5.5, and in this case also the same case, same situation. So in both of them, in both the graph, in both graphs, we have mean, median, and what about the most probable value? Is it same or not same?
Not same.
It's same.
Same,
Most
sir.
probable-
5.
Most probable value is same. No, this is the most
The
probable
middle value.
This is this value only, that the maximum probability. So this is the maximum probability in this case. This is the maximum probability in this case. We are not talking about the value of the probability. We are talking about the
Okay.
maximum, like which value has the maximum probability. Okay, so mean, median, and most probable value. Most probable value are same. All right. So how to distinguish between them now? In both the graph, we can see clearly that there is difference, but whatever statistical like tools we have discussed till now, mean, median, most probable value, all are same. Like all are same in both the cases. So how to distinguish between them? So there is something, if you see carefully, the spread of data. In this case, the data is not spread out too much. It's about the mean. All right. Now in this case, it's spread out over a larger range. All right. So we'll define something. We'll define something to measure the spread. So to measure the spread, of data. So this is not a technical term, but we can talk about it in English. All right. So this is spread of data. Now, how do we measure this? So there are what we can do is, okay, we can define x, and we can define a quantity like this, where we take x is equal to j, the quantity j minus this. All right, in this case. Now in this case, let's take an example. Let's take an example of this data, 9.1. All right, now this is say 9.0, 8.9, and this is 9.2 and 9.3. These are the values given to you, some variable x. So what is the mean here? What is the mean here? What is the mean here? If we
Sir,
take
9.1, sir.
9.1.
all right. So what we can do is, let's define this spread by this quantity. So is it feasible? Let's see. So this is 0. If we subtract x by subtracting this column with this value. So this is a constant quantity. Mean of x is a constant value, but x is a variable. So if you subtract this one for each value, what do you get? This is minus 0.1. This is minus 0.2. This is minus, this is 0.1, and this is 0.2. Now, if we sum over them, sum over this value, so what will you get?
0, sir.
So there is not much of an use. All right, if you add them and you get 0, this is not much of a use. You could have instead taken a mod. You could have taken the mod of this value, but mod functions are difficult to handle sometimes. All right. So what we do is we define something called x minus x whole square. All right. And when we find this value and then sum them, it won't be 0, and that will give us a measure of what is the spread of a graph. Now in this two we'll get the different cases. In these two cases it will be different. All right, because the value this value will be different, x minus x mean whole square. Now this is called the what it is called variance, right, or standard deviation.
Okay, sir.
So this is what we calculate. This is what we calculate. We'll calculate this. We'll calculate this. All right. So this will be non-zero. If you add them, this will be non-zero. You can check this if you want to calculate this and see this. Take this will be 0. This will be 0.01. This will be 0.04. This will be 0.01, and this will be 0.04. Now if you add them, if you sum over them, so what will you get?
0.1.
So if you sum over them, you'll get sum over all these values. So let's bring this thing here. This summation over x minus this will be 0.1. All right. So this is how we can find the measure of a graph. All right. Now let's define this quantity. This is say delta j is equal to j minus j mean. All right. And let's define this quantity as sigma square delta j whole square is equal to, this is j minus mean whole square mean. So this quantity is called variance. All right. Or if we find out sigma, so this will be given by this quantity. And this one is called standard deviation. So this gives us an idea of how much the spread of the graph is. All right, how much away from the mean position the other data is. So let's simplify this thing. Now let's write something called, which is standard deviation. Standard deviation. All right. So this is the square root of mean of this value. Now, how do we define this thing? All right. How do we simplify this thing? Let's. This is a very interesting calculation. If you see this, so we have j minus mean square. Sorry. Square. Yeah. Now let's simplify this. Now, how do we write this? What is the definition for mean of some quantity? How do you write something? If you want to take a mean of j, how will you write? Summation j pj.
pj.
Right. Now, in same way, here what is given to you? Here the quantity is this. So how will you write the mean? Now this bracket is a mean. So mean of this quantity, how will you write? Summation j minus j mean whole square pj. Right? Now, in this case, summation, if we now let's square this j square plus mean j square minus 2j mean. All right. and then we have pj, this simple whole square of this quantity. So if we just take the summation and pj inside, what do we get? So j square pj plus summation j square mean square pj, all right, minus summation, so let's bring 2 outside, okay, and see this quantity, this for a given set of values, j mean is a constant quantity. Now this can be taken outside the summation, this won't change for a given data. So j and this 2 and mean of j will come outside the summation, all right, and this will be written as j pj, right? Now let's see what do we get. This will become what? How can we write this quantity? This will be mean of
Mean j
j
square.
square.
Yes.
And then what is this? This quantity is also constant quantity, right? This can come out of the, now mean is constant quantity, the square of mean will also be constant. Now this will come outside the summation and we have pj minus, this is mean j, and this will be what? Mean of
In J.
j. So this becomes j square plus j square. Now this is what? This is 1 minus, this is 2j square, mean j square. Now you can see this quantity and this quantity are same, all right, so you'll get j square minus, this will be minus mean j square. Now this is a very this is the formula which we'll be using for standard deviation, all right. This is what we should remember, j square minus j mean square. So these are 2 different quantities, j square mean and mean j square. Now we'll come to the difference what it is. So this is a simplification of the formula which we found out earlier, and this is used to find the uncertainty in some cases, all right, and how this is how we define uncertainty in some calculations, all right. Now let's see the differences between, like, these two they are different quantities, okay. Let's see what are the differences. Example, two child in a room with age 1 and age 3, all right. So we have two child in a room with age 1 and 3, okay. Now what will be the j square mean? This is 1 square plus 3 square by 2 is equal to 5, and what will be j mean square? This is mean will be this, and whole square, this is 4. We can see both are different things, all right. These two are different things, okay. So with this example you can understand what is the difference. Now standard deviation is defined. Now this is an important point to remember, that standard deviation is defined as a positive quantity, all right. So now there is a question based on this in TIFR as well as I think some BHU, I guess, yeah. Actually TIFR gave the question first and then BHU took it from there, all right. So somewhere so this is a very important point, and there was a question asked in on this, all right. We'll do that. Now next point is equal to will hold when sigma is equal to 0. Now I hope everybody is making notes, all right.
Sir, we are having notes. We are doing notes.
Yeah, so please make the notes. That is how you interact with the topic. So this is all data values are same. Equal to will only hold when sigma is equal to 0. Okay, sigma is 0, that means we can write like this, both the quantities will be equal, then only sigma will be 0, and sigma 0 means this all values, data values are same, that is why we are getting 0. There won't be any spread, nothing will be there, all data are same, so mean, median, mode, everything will be same. All right, now let's go to this was all discrete system. Let's move towards continuous system. All right. So in this case, we'll define something which is probability of an individual having age in range, all right, x and x plus dx. All right, if you try to calculate the probability here, so this is like we have rho. Now we'll define something here which is different from the discrete part a little bit. So this is rho x dx. Now in this case, we don't call this rho or p, sometimes written as p also. We don't call it as a probability, we call it as a probability density. We have to multiply it by some unit length or unit area or unit volume to get the total probability in that range. Now probability of having, let's continue with the same example of the age. Let's say we have a uniform distribution of ages. Okay, so probability in that case, probability of having any age, probability of having any age. So this will be rho x dx. If we can have any, like we just let's say we go to a street and ask everyone about their age. So it could, if we have a range, a defined range, all right. So if you try to have any any age, so this will always be equal to 1. All right, this is what is called this is how we define the probability density, that if you try to get any age, this should give us 1. Okay, so this is basically the normalization condition. We try to get the values of probability between 0 and 1. All right, now we'll discuss this in terms of quantum mechanics also. Now this is just the introduction part. Okay, so what are the
Sir?
Yes, tell me.
Could you please explain the normalization condition? Why is it called so?
Normalization condition, because see, what we are doing, we are just like whatever the values are coming out, like say why it's called so, I'll discuss when I discuss the normalization condition. There is a better example there. All right,
Okay.
I'm not getting into that example right now. The normalization thing is that you are trying to get the total probability. Okay, whatever the probability you are calculating, we're
Okay.
using probability density, it should lie between 0 and 1.
Okay.
All right, the
Okay.
value should lie between 0 and 1. All right.
Okay, sir.
Oh yeah. Now let's discuss this mean of x. All right, mean of x. How it's defined in a continuous variable case? This will be mean x is equal to, now x and multiplied by the probability density integrated over the small element dx. This is how it's defined for a continuous variable. All right, now mean of any function. mean of any function, mean of fx, all right, any function of x. This is fx is equal to fx rho x dx. Wherever we had x, we had put here fx, all right. So this is the general formula to get the mean of any function of a continuous variable. Now let's do a question which has been asked in TIFR 2016. Let's write down the question. So it is, if x is a continuous variable, all right, which is uniformly distributed over the real line from x equal to 0 to x tends to infinity according to the distribution function, all right, f x is equal to exp exponential minus 4x, all right. Now then the expectation value of cos 4x is, all right, so we have the options. This is from TIFR 2016, all right. The options are 0, this is 1/2, and we have 1/4, and D 1/16, all right. So this is given to you. So so what they are asking now, we have to first make sure. Now this rho is also known as a distribution function. This probability density, this is also known as distribution function. This is other name, which is called distribution function, all right. Now in this case, what we have been given, the range is from, the variable is from 0 to infinity, and it is a continuous variable, all right, and the distribution function is this, all right. So we have to first see whether the distribution function it follows the normalization condition or not. Okay, this is the solution. So let's see whether like if you find, let's calculate. This is fx dx should be equal to 1. So this is a normalization condition. So let's see if it holds. Like the normalization condition should hold, so that we can further calculate the probabilities and whatever is required. So in this case, let's see if it's 1 or not. So if we take exponential minus 4x dx from 0 to infinity, what is the value we are getting? So this will be what? You just take minus 1/4 outside. So this will be minus 4x 0 to infinity. This is minus 1/4. This is 0 minus 1. This is 1/4. So this is not equal to 1. All right, this is not equal to 1. So we need to normalize this function. So how will you do it? Now in this case, let's say that fx is a e to power minus 4x. There's some constant. Now this is a constant value, right? The whatever we have got here, 1/4. So if we somehow multiply and divide by something here, okay, so we'll get the a normalized function. So we have to normalize this. So let's assume that this is the distribution function, and this is the normalization constant. Okay, this is the normalization constant. So this is a purely mathematical thing. Okay. Now in this case, if you just put the values, what should we get? We have to find a such that if you integrate over 0 to infinity over this distribution function, it must be equal to 1. Now if you solve this, a comes out. What do we have? E to the power minus 4x dx is equal to 1. Now we have already calculated this part. This part is how much? 1 by 4. This gives you a is equal to 4. So finally, the distribution function, the normalized distribution function. So we can write like this: fx normalized, all right, is equal to 4 into e to the power minus 4x. So this is the normalized function. Now, after the normalization happens, after this function follows the normalization condition, then only we can calculate any other statistical quantity using this function, using this distribution function or probability density function. All right. Now we have been asked that we have to find out the expectation value of cos 4x. We have to find out the expectation value of cos 4x. Now we have seen how to write down the expectation value of any function. Say let's have gx. So if you write down the expectation value of this, this will be written as gx and multiplied by a distribution function and dx, right? So in this case we have cos 4x. So we'll get, this is cos 4x, all right, the function itself, and the distribution function is 4 e to the power minus 4x dx, and the integration is from 0 to infinity. All right, so you have to do this integration. Now there are many methods to do this integration. Like in coaching center where I used to teach, I did this calculation using 4 methods. Okay, so one of them you can do is using Laplace transform. Now Laplace transform we have discussed in this course, but some of my students already know what Laplace transform is, so we can use that. All right, there is another technique. Okay, so I will discuss another technique. Laplace transform I'm not discussing because I have not covered in this course. So let's teach you something. So if you have this format, if you have cos x and we have say ex dx. Now how to do this calculation? This is the integration given to you. All right, this is the integration given to you. How to do this kind of calculation? Okay, so what you do is, for this is one of the tricks. This is the third form of that. This is the form 3 of that integration technique I taught you. Okay, so if you have a power 1 of this cos and there's a power, like there's no power on the x, if this is the format, this could be sine also. Now in that case, how will you do the integration? Now this is the trick. What you do is you write like this. So this is differentiation, this is integration. All right, so let's write this e to the power x on this side and cos to the power x this side, cos x this side. So in this case, now this method I'm trying after a long time. I did it in like maybe 12th standard or I don't know. Let's see, I thought now only that let me try with that. So if you integrate, now if you differentiate this will be e to the power x. Now if you integrate this will be sin x.
Sin x.
If you differentiate this will be ex, this will be minus cos x. Now you have to stop where this, again the same function comes. You have to stop here. Same function again repeats itself. Okay, you have to stop here. Same function appears, so you have to stop the process. Stop integrating. So this is the same function, only a minus sign is there. All right. So again, you have to like draw the technique is similar to that, which we have previously done. You will connect these two, okay, and you put plus minus, and then here you have this thing, and this is plus sign. Okay, you connect like this. Now in this case, what is happening here? So I is equal to, you write like this. This is, you just do whatever we have done earlier, plus plus plus. So this is ex sin x. Okay. Now then we have my plus, this will be plus minus, this is e to x cos x. Okay, and then we have minus, now this is ex cos x dx. Now this is same as what? This is same as I. Right? So you can take this minus I to this side, this will become 2i is equal to ex sin x plus ex cos x. All right. So this will be I is equal to ex by 2. All right, and this is sine x plus cos x. All right, let's see if the calculation is right or wrong. If you differentiate this, we should get the initial function. So see if it's coming out or not. Let's differentiate this and see, check the method is correct or not, because I'm doing it after a long time. It might come out to be wrong. Let's see. So this is ex sine x, and then we have plus ex cos x. The next term is plus ex cos x, and then we have minus ex sine x. So if you cancel this out, so this is again, this is ex cos x. So voila, we have this result. So we did, the method was right. I still remember a few things long time back, from long time back. So this is the integration we had. This was a function we had to integrate, right? So this method is correct. Now apply this to this function. This function, take this and apply this to that. So we have this thing, this function is given to us. So everyone do it. It's very interesting to do this calculation this way. So we have cos 4x. Okay, so let's write down the integration. This is minus 4x cos 4x dx, 0 to infinity. All right. So if you use the Laplace transform, it's very simple, but Laplace transform it takes time to learn. Okay, so if you don't know Laplace transform, you can do it like that. So just write down the functions. This is e to the power minus 4x. This is the integration. So this technique was not there in the video, earlier YouTube videos. All right.
Yes, sir.
Cos,
It was not the.
yeah. So I told you, you'll learn something new every time, even though the syllabus is same. So this is, if you differentiate this, this will be minus 4x, this will be minus 4x, and then we'll have again 16 e to the power minus 4x. Now in this case, we'll have 1 by 4 sine 4x. All right, then we have minus 1 by 16. This will be cos 4x. So we stop here. All right. Now, as soon as we get back the original function, we stop here. So this is, you connect like this, and the final one is like this. This is plus, this is minus, this is plus. Now let's write down the integral. So this is, let's label this to be I. This is say 4i. Okay. So this is 4i is equal to, now this will be 1 by 4 e to the power minus 4x sine 4x. All right, minus, this is 4 by 16 e to the power minus 4x cos 4x. All right, minus, this is e to the power minus 4x cos 4x. All right, and now this is a limit. There is a definite integral, so I'm not writing down the constant. Okay, because we have to put the limits also. Now this will have an integration sign. The last integral will have an integration sign. Okay, the last term will come with an integration sign. So this becomes, so let's see what do we get. This is 1 by 4 minus 4x sine 4x minus 1 by 4 e to the power minus 4x cos 4x. All right, minus, now this is I. All right, so let's bring it this side. So this is 5i is equal to, now there is a 1 by 4 is common here, e to the power minus 4x sine 4x minus, this will be e to the power minus 4x cos 4x. All right, now divide by 1 by 4. So this I is equal to 1 by 20, 1 by 20, and we have e to the power minus 4x sine 4x minus, this is e to the power minus 4x cos 4x. All right, so this is 0 to infinity. All right, let's see what you get. This is, what are we getting? So this is, now we always know that when we have a function multiplied to another function, exponential function multiplied to another function, that exponential function dominates. All right, so this is a thing which we have, some of you know already. which you have learned in some other classes from me. So always remember that whenever you have an exponential function multiplied to a normal function like this, exponential function dominates when the values are large. So when you put infinity here, this term, whole term will go to 0. So the first term, this will become like, this term will go to 0 in the upper limit. So let's put it to be 0. Mine now next term is also 0. All right. Now minus this term is this is again 0, because this will be 1, this will be 0. All right. Now this one is 1, this is 1. So we have this result. All right. So did we make any calculation mistake here? Let's see. So what do we get? This is 1 by 20. I don't think we should get 1 by 20.
1 by 2 आ रहा है सर यहाँ पे, जहाँ पे आपने 4i किया है ना, 4i किया ना, यहाँ पे i होगा
यहाँ पे।
हाँ, फिर ये 2i हो जाएगा, उधर
नहीं,
जाएगा
यहाँ
तो।
पे 4 मैंने इसको i लिया ना।
हाँ, तो आपने इंटीग्रल को i लिया ना, 4 तो उसके साथ मल्टीप्लाइड है।
अच्छा, ओके ओके, सॉरी। सो ऑल राइट, यू आर राइट। सो हमें i निकालना था ना यहाँ से। यू आर राइट। So this will be not this thing, this will be 2. You're right. So this will become 8. All right. So this is not 20. So this is 8. Now this is 1 by 8. Now the integral was 4i. All right. The mean was equal to 4i. So this is cos 4x. This is equal to 4i is equal to 4 into 1 by 8. This is 1 by 2. All right. So there was a calculation mistake there. So this is the answer. Which option is it? I think it was
B.
B. All right. So correct option is B. But in exam, you can apply Laplace transform. So in this case, it will be, if you apply that, if you know Laplace transform, it will be very simple to do it. So let's do that also. So this is cos 4x dx equal to, what is the question mark? Now this is 4, 0 to infinity. So if you try to take the Laplace transform of cos, what will you get? This one. Laplace transform of cos 4x will be, anyone?
Sorry, s by a square plus a square.
S by, no, so S is S by S
S square plus 4 square.
4 square, right? This is S by S square plus 16.
16.
All right. Now the thing is, in this case, now this is a function of S, right? Now in this case, if we have this quantity, so this is basically, this is equivalent to writing, let's calculate this quantity, 4x cos 4x. So this is what? This is S, this is kind of S here. Now this is A, right? So this will be like, this will be S by S square plus 16 at S equal to 4, right? So this is 4 by 4 square plus 16. This is how much? This will be 16, this is 1 by 8.
1 by 8.
And then we had this 4. This was the integral which we took. Now this is equal to 4i. So this is equal to 4i, which is 4 into 1 by 8. So this is the method 2. Method 2 using Laplace transform. This is 1 by 2. All right. So there are other methods also. Let's not get into it. Now this thing, let's do this plotting. Note, we have fx is equal to f, say we have this format. We have this format where this is gx e to power minus x. Now, some of you already know this thing and some of you don't. So just listen to it again. So if for small values of x, fx will be proportional to gx. All right, fx will be proportional to gx. Now, for large values of x, now whenever I say large values, it's away from 1, like more than 10 or something like that. and for small values it's like close to 0. All right, so this is proportional to minus x, the exponential function. All right, now in this case, let's do this plot. So y is equal to e to power minus x square. Y is equal to e to power minus x square. So if you want to plot this, you like the plot is a bell-shaped curve, right? The plot is a bell-shaped curve. All right, this is the plot of this 0, 1, and because we know at x equal to 0, y is equal to 1, and x going to plus minus infinity, this is an even function, this y will go to 0. All right, so this is how you get this, and the slope here will be 0. You can differentiate it and put x equal to 0. You'll find that the slope is 0, so that this will be a smooth curve. All right, so this is a bell-shaped curve. Now if you want to draw this graph, x y is equal to x e to power minus x square. All right, so in this case, if you see that for large values of x, which term will dominate? So y will be proportional to e to power minus x square, and for small values of x, y will be proportional to x. All right, so this is how we can draw the graph. Now what happens at x equal to 0? X equal to 0, y will become 0, and x tending to plus infinity. All right, so x tending to plus infinity, what will you get? Y will tend to 0, and x tending to minus infinity, y will tend to 0, but from negative side. All right, because the next x will be negative in that side. Now if you draw this graph, so we have seen this, that for small values of x, for near 0, the y behaves as a straight line. So this is a straight line. Now for large values of x, it's exponential to the power minus x square. So this large values, the exponential part will be like this, it goes to 0, and in this side it will go to 0 from this side, because there's a x multiplied with the exponential term. So this terms will be, the values will be negative. Now if this is increasing, this is decreasing, there will be some maxima out here. So this is how it will close, and one can also differentiate it and see that there's whenever where there's a maxima value, the curve is the slope will be 0, and hence the curve is smooth. And in this case, if you connect like this, so this is the curve you get. So this part is y proportional to x. Now this is very important when you do harmonic oscillator problem. Okay, you get this. You have to know this plot. Okay, how to draw it. Okay, and so this part is minus exponential. Now this part is proportional to minus x square, but with a minus sign. All right, and so you can draw the graph like this. All right, now let's talk about something called superposition. All right, now I thought like 40-minute lecture is too small. All right, so that's why I increased the time, and it's better to discuss, otherwise we are in a hurry that okay, there's 40-minute time limit, meeting can end anytime. All right, so I increased the time limit. So in this case, superposition. Now let's discuss what happens in now there are, we have been doing this superposition thing from whenever we started with physics. All right, so in our school, but we didn't call it this way. So superposition is in classical physics. All right, now while we are speaking on Zoom, there is a superposition principle in activity. Okay, all right, I'll tell you what it is. There are many, but one of them is what I'm going to tell you about. So superposition of two physical quantities. Now this superposition we are talking about the classical physics gives a third quantity which is completely different from the initial two quantities. All right. So it's very simple, straightforward. You have two quantities, you have two physical quantities, you add them and you get a third quantity which you don't have any information about the first two. All right, you lose the information. All right. So let's talk about something we all know, that waves. All right. So let's talk about the waves, a pulse. Okay, as a square pulse. So we have this pulse. All right. Now plus this one is there are two pulses, both are same. I assume the diagram is not matching, but I'm assuming that both are same. So what will we get? What is the resultant? What will be the resultant of these two pulses? Now both are superimposed.
Amplitude increase.
Amplitude will become double.
It will be twice.
All right, it will be twice. Now this kind of we call this interference is called constructive. All right, so it's adding up. Now if we have a similar situation where this is the graph given to you, all right, and we take this plus sign and then we have this a negative pulse of same amplitude and okay, so if we add them, what will we get? It will
be zero, sir.
It will flatten out. So destructive interference. All right. Now, so we can see that if I give you this only, if I give you this wave only, can you tell, is it possible for you to tell me which waves it was made of?
No.
Okay, you cannot figure it
Sure.
out. All right. And this one is also the same case. You cannot tell. It could be any amplitude. It could be any pulse. It could be sinusoidal pulse. It could be square pulse. It could be rectangular. It could be triangular. Okay, so we do not have any information about these initial two. So in classical, we do not have any history of this whatever it was made of. Okay. Now, note that this is an important thing to note. Now this is how you learn the differences in quantum mechanics and classical mechanics. We are already learning this thing now. So classical superposition. In classical superposition, all right, no information about the initial physical quantities can be found out from the resultant quantity. We don't have any information about that. All right. Excuse me. Now, let's talk about quantum superposition. All right. Now, in this case, I told you about this. I told you about the example of Zoom call. Now, in this Zoom call, there is something called noise cancellation. All right. There's active noise cancellation. While we speak, while I am speaking, the surrounding noises are suppressed. All right. Now, this is a different technique to do. But when you take a headphone, a noise cancellation headphone, active noise cancellation headphone, in that, what happens is there's a audio signal which is reaching your ear, and there is an audio signal which is which is coming from your mobile phone into your headphone, and there is a surrounding noise which is also coming to your ears. and near that cup, headphone cup, there is my mics also. Okay, if you have a good active noise cancellation headphone, in that case, it takes in the input, the surrounding noise, and it knows that the signal of the mobile phone, it knows about the song we are playing. So what it does, it's just it superposes the external surrounding sound as an out of phase into the sound you are listening to. Okay, so that is how it cancels the noise out of it. Okay, and you can only listen to the song. So this is how this principle is being used here. This is being used, right? So that is quantum classical superposition. Now let's talk about the quantum superposition. Quantum superposition. All right. So can you hear? There was some noise right now from my end.
No, sir.
So
yes, sir.
But there was
Yes,
noise
sir.
actually. That's a auto passed by near my house. Okay. So, but you couldn't hear it much. It was sometimes audible, sometimes not. Okay. So that is the active noise cancellation happening. Okay. Now, but this is the technique used here is different. This is something I think deep learning. They are using deep learning methods or machine learning methods to do it, because I'm not giving them any other inputs. Only this single mic is there, and in headphones there are several mics, and there is a different input altogether. Okay, so there are different technologies. Now, in quantum superposition, let's what it is. Let's talk about it. So, example. Let's take a hadron electron in an atom. So this an electron in H atom may be in ground state, or first excited state. Maybe in ground state or first excited state. Now let's make it a little bit colorful, otherwise it's completely black. So first excited state. All right, now it could be either in that too. So this is these states are known as pure states. Pure state. All right, pure state or definite states. All right, but the electron can also be, now this electron can also be in quantum state, which, or this is called mixed state. All right, this is called mixed state, which is superposition of of ground state and first excited state. First excited state. All right. So this could be, there are two things. One is that it could be either in the ground state, in the first excited state. So these are called pure states. Okay, these are called pure states. Now, pure state or definite states, and that could be a mixed state. Okay, the other could be a mixed state. So this is a superposition state. All right, where we can have the superposition, like it could be in the ground state and the first excited state simultaneously. All right, but it depends on when we measure what happens. Now the next is, let's take an example. Now this is a classical example, but we'll try to think of it as a quantum one. To some extent it can be, and it is analogous to the quantum system, but let's take a unbiased coin. Now what do you mean by unbiased? Any idea?
Equal probability of getting heads or tails.
That is mathematically, but physically, everyone, like, no, many of you asked about physical reference. So
Sir, it
Not the
has
default.
uniform mass density.
yes, very good. Mass distribution, uniform mass distribution. So this means the unbiased means the mass distribution is uniform. Uniform mass distribution.
Sir,
Yes.
does it mean uniform mass distribution in quantum mechanics context, or always it means that?
No, unbiased. When we talk about in probability, when we talk about an unbiased die or unbiased coin, in that context.
Okay.
This example is like it's a classical thing, because you can always, if you toss a coin,
Yeah.
you can always find out with all the, if you have all the parameters, if you try to make a calculation that what is the state of the coin while flipping, while it's in the air, and at a certain point, at a certain time, you can get it exactly if you put in all the parameters, like velocity of the wind outside it, and what is the weight of the coin, what is the flipping speed, okay, what
Yes,
is the
sir.
angular rotation. A lot of parameters you put in, you will find out. Classically, you can answer the what at particular time, what is the state of the coin.
Okay.
Right. So that this is not a you are using the classical example, but it gives you a visual picture, okay, which is not exactly true, but you get a feel of what quantum mechanics does. All right.
Okay, sir. Okay.
So that is why I'm using this example. So in this case, let's the state. Now we'll use this symbol, which is a famous one, which is Dirac notation. This is called a Ket bracket. Okay, we'll discuss this afterwards. Oh, I'm just using it here. Now there are two states, right? There are two. One is the tail, and other is the head. Now either of the coin could be in either of them. Now there's something called which does not have any relationship to the mathematical world. This only comes in the physical thing. Now this quantity is called the probability amplitude in physics. Squaring this gives you the probability. Now this has no background in mathematics. This was discovered in physics. All right. Now squaring the amplitude in this case, now if we square the amplitude, now this probability amplitude, if you square this, squaring, now this fact that there is no mathematical background of this probability amplitude term, I came to know only 2 years back, all right, when I was teaching quantum mechanics. So quantum mechanics has a lot of books. One book will not answer all your questions. Some book is good in something. All right, so that is why there are so many good books in quantum mechanics. Every book you pick up, you learn something. So squaring the amplitude gives us the probability of finding a given state. All right. So this is when we square this. Now we'll come to this later on. We'll discuss this more. Just think of it that there's some number which is associated with each state. When you square them, now we all know that when we have a coin, there's a 50-50 probability of each of them, head and tail, right? So if you square them, this will give you 1/2. This will give you 1/2. So that is the probability of getting each of the states. Now, when you toss it, when it's in the air, it's a superposition of both head and tail. Let's imagine it is actually classical. It is a classical thing. You can of course measure it with some, I told you earlier, but let's say we cannot do it with some, if we do it right now, if we toss this coin, we cannot tell which side it is at a given time. Okay, exactly. So let's assume that it's not, we cannot do it, but when it lands on our palm or on the floor, let's say when the coin is on the, now this pen starts misbehaving after 1 hour. All right. So I don't know why. So when coin is on the palm, okay, and you see the coin, so that means you are making a measurement. Once you see, you're just getting it on the palm, you can see one of the various states, you're making a measurement. Now, and at that point, we can say that the state of the coin is 100% with 100% probability, it's head, say it's head. All right, so this is the amplitude, probability amplitude, and that becomes 1. Now, we can say that this whole process is kind of a measurement. This is the kind of a measurement you are doing. You're getting it on the palm, and this is a measurement. This is a measurement. All right. Now we say that measurement destroys superposition.
Sir,
Now, these concepts will help you understand some questions. All right.
hello, sir.
Yes, tell me.
Sir, when it is in the air, it is in the superposition of head and tail. When it is in the palm and we haven't yet seen it, what can we say about it at
It's
that
also
time?
if you are not, if it's in the palm and if you're still not opened your if you still not opened it to see it,
Yes, sir.
okay, then it's still in the superposition.
Okay, sir, but isn't that some kind of interaction when we catch it in our palm?
Yeah, Sayed, see, this is just a approximate analogy of a situation in quantum mechanics. It's not exactly replicating whatever is there. Just think of it as that there's some, we are trying to, there's a system which we say that this is, it's in the superposition state when we are not able to exactly determine it. But when we, it's on the palm, yeah, of course it has a definite state, but we don't know about it unless we see it.
Okay, sir. Okay, sir.
All right. So
Yes.
in this case, the measurement destroys the superposition. Now this is very important from quantum mechanical point of view. The measurement destroys the superposition. All right. This is an important statement to remember. All right. Now, if you think that this, yeah. So in this case, so coin, the state of the coin can be written as this tail and some beta head. All right. If the coin is unbiased, if it's biased, then alpha and beta will be different. It will not be equal. All right. So we can also do the alpha, and in this case, in quantum state, the alpha and beta can be complex numbers. Complex numbers. All right. So we'll come to this in more detail as we go on to do operator algebra. All right. So this is how a state is defined. Now let's take a very famous example, which we as students were very fascinated about whenever I used to hear about it. Schrodinger's cat. Now this is one of the various situations of what I'm going to do is it's one of the various situations which can be used to describe the Schrodinger cat. Okay, so let's see if I can get a cat done. All right. So say this is a cat given to you. All right. Now somehow I'm able to get it. All right. So let's say it's a cat. I don't know what it is. So if it's in a box, all right, if it's in a box, so let's draw the box. It's in a box. Now this is one of the simplest cases which I'm going to discuss. So in this case, say now this cat is a classical system. All right, this cat is a classical system. Now in this case, say we have a uranium-235 radioactive element. All right. Now in this case, say there is only one atom here, one radioactive atom, one atom. All right, and this is the box. All right, and this is closed. Okay. Now we do not. Now this is a quantum system. This is a quantum system. And there are a lot of more complex systems for Schrodinger's cat. Okay, this is a very simple one. So what quantum system, what we do is if it emits this is a radioactive atom. Okay, this is a radioactive atom. So it emits, decays into some particles, and that particle hits this, and the cat either lives or dies. All right. So this quantum system makes this whole thing quantum mechanical. All right. The outcome of whether the cat is alive or dead becomes quantum mechanical, even though the cat is classical. Now, in this case, the initial state of the cat, okay, when we put it into the box, all right. So it is after the box is closed, we have this state that cat is equal to 1 by √2. Let's say this is a 50-50 chances of the emission. So this is 1 by 2, this is alive. Now this is called the mixed state. When we have a superposition, that state is called mixed state. All right. Now when the box is opened, all right. So in that, we say that this is a measurement you are doing. So we see, let's keep the cat alive, let's not kill it. So in this case, what we have is we open and see that it's alive, and the probability becomes 1. Okay, so this is a definite state. This is a definite state or a pure state. Definite state, this is called definite state or pure state. Okay, now the probability here, probability of finding the cat after the measurement, in this case, probability becomes the probability amplitude square. So probability is amplitude is 1, your square, this is again 1. Now what is the probability of finding the cat alive in the earlier case? If you take this state from in this question, what is the probability, if I tell you what is the probability of finding the cat alive? All right. So this will be equal to 1 by √2 whole square is equal to 1 by 2. This is 50%. Right. Now this is just an example question. Now, so what we'll do is we'll start in the next class. We'll start de Broglie waves. Or let's how much time do we have? We have 7 minutes. Let's start a brief introduction. All right. So this will be de Broglie. Let's start our de Broglie waves. All right. So de Broglie wave is something like which was proposed by. Now, how do you pronounce this thing? If you the person who gave this hypothesis.
Sir?
Yes. Tell me.
Louis de Broglie.
Above example, is it also an analogy or is it a real quantum example?
Which one? This
So
one.
The cat
This one.
example.
What is the probability of
which you have
finding the
given.
cat alive? Or this whole example, Schrodinger's cat.
Yes, sir. Yes, sir.
The Schrodinger cat is also like it is a quantum mechanical because we have a quantum mechanical system associated with this.
Sir, but then why didn't you write alpha and beta, rest to that, sir?
We are assuming that it's 50-50 chance, assuming that the equal probability is there of each state, assuming equal probability.
Okay.
All right.
So by which you're making it a classical system again?
No, who said that? A electron can have a 50-50 chance of being in the ground state as well as the first excited state. All right.
Okay, sir. Okay.
It doesn't, if you have two equal probabilities, doesn't mean that it's a classical system. All right. So it could be a quantum mechanical system. So the Louis de Broglie was a prince. I don't know why he wanted to do physics. All right. So he did his PhD on this thing. He did his PhD on this hypothesis, okay, de Broglie wave, and he was just 24 years of age that time. And so I used to think this is a big, huge deal to write a paper, but this was a very big discovery. All right. And when we were in IIT Kanpur, like people who entered IIT through 12th standard after IITJAM, they had they started like publishing research paper in the second year itself. All right. So they are I think 18 or 19 years of age at that time. I first published my paper at the age of 23. So I used to think it was a big deal, but it's not if you see your age also. But you have to be in the right place and the right institution to.
So on which topic you have published it?
Mine starting when I was in MSc, it was basically I did research on the high energy physics, so it was very special relativity. Okay, there is special relativity and there was very special relativity. So that was the first one paper which we published, and then I switched to fluid dynamics. All right. So there also I have one paper, and two papers was about to be published before I dropped out. All right. So let's not go there. So in this case, so this is pronounced as Louis de Broglie. All right, but Louis de Broglie you can pronounce so that you don't make a spelling mistake. So what at that time was during that time when they gave the hypothesis, everyone was very fascinated about the particle nature of the photons. All right, so everybody was behind this thing. In scientific community, this happens. One thing is discovered and everybody goes behind it for a long time. All right. So everybody was crazy about the particle nature of the light. Now, de Broglie thought that what about if we consider the wave nature of particle? All right. So this was a change in thought at that time. Okay. So this is h is the Planck's constant. All right. So let's give Planck some respect. Let's make it P capital. So this is Planck's constant. All right. Now this is equal to 6.626 into 10 to power minus 34. Now this is a quantity which you will always come across in a quantum mechanics. There is small c, which is the speed of light. Now this is meter per second. Okay, so speed of light. Now it's going to become tough during this Diwali to take lectures, give lectures. Now wavelength, lambda is wavelength of light. All right, lambda is wavelength of light. So if we take the photon case, what is the momentum of photon? E by c, right? Or we can write this as, if we take this further, we can use the formula for energy. This becomes hc by lambda and also divided by c. So this is basically h by lambda. Now this is the momentum of a photon in terms of the wavelength. Now the same argument was made in case of particles, that by de Broglie, and it was later proven right by a Deviation German experiment. Okay, they got that electron showed diffraction behavior. Okay, so in this case, the elementary particles, he said that the elementary particles may also show wave behavior. All right, so with lambda is equal to h by p. Okay, so let's stop here. Okay, and in the next class we'll again start with this. So any questions? Hello.
No,
Sir,
sir.
is this
No,
wave
sir.
real or not? What
No,
type
sir.
of wave is this?
See, this wave is like, see, the thing is there is a very this wave and particle are construction of English language. Okay, this is a very old language. Okay, English. Now quantum mechanics is a recent thing. All right. So in that case, whenever we hear about a particle and whenever we hear about a wave word, whenever we hear about particle, the picture comes to our mind, very rigid, spherical, like a billiard ball, okay, a ball, okay. So these are the objects which comes to mind whenever we talk about particle. Now, when we go for the waves, we always see the sea waves, okay, sound waves we cannot see, but we can see water waves, all right. Waves on a rope, we can see that. So we have a different picture of that. Now, when quantum mechanics comes in, there's a confusion, because the electron, the part which we thought particle, behaves as in diffraction experiments, it gives interference patterns and diffraction patterns. All right. So there's a confusion, like what to call. Now in physics, what we do is when we have some experiment, we try to explain that using some mathematical model. Now, when we found that the electron showed you that there was diffraction pattern coming out of it, that means we can treat that object, that whatever this electron is, like a wave, right? Now, it is a mathematical construction. Okay, we do not know exactly but we know that the outcome is that of a wave. All right, so we are constructing it mathematically. All right, right. Let's sign off then.
Sir, will the classes be 1.5 hours from now?
Yes, I've given you the days, and so that we'll complete it on time.
Okay, sir.
40 minutes, it's very less.
Okay, sir.
All right, and we have freedom to ask a lot of questions, doubts, discuss them.
Okay, sir.
All right. So is it okay with everyone?
Okay, sir.
Yes, sir.
Yes, sir.
All right. Thank you so much.
Thank you, sir.
Thank you for watching. Have
Thank
a
you,
great day.
sir.
All right.